Good afternoon. I'm Lisa Van Loon, the founder of Lisa Can Analytical Solutions, Inc., a boutique analytical solutions provider. My goal is to provide critical knowledge that allows for real-time decision-making using innovative technology, adding value in mineral exploration, processing, and remediation. Since 2017, I've been working with Neil Banerjee, Stuart McIntyre, Mike Bauer, and Nathaniel Sherry to innovate XRF fitting, particularly for synchrotron-based data. The result is Peakaboo. Today, I'm delighted to show you some of the most important innovations, how easy and intuitive it is for new users, and I'll share examples from earth and environmental sciences and archaeometry throughout. Our group has a number of other presentations here at the conference. In particular, Stuart McIntyre will be giving a platform presentation in session A076 on Peakaboo's quantitative analysis feature, and a poster session in session A08P1 on August 5th using Peakaboo's correlation capabilities. There's something a bit different. On August 5th, I'll be presenting a poster on research being done with collaborators from the Royal Trail Museum on using synchrotron micro-CT to study fish fossils. The software can be downloaded from www.peakaboo.org. So why develop a new XRF analysis software? X-ray fluorescence is a well-known method for the identification of chemical elements in materials. The incident X-ray excites an atom which subsequently emits fluorescent X-rays with energies that are characteristic. This means XRF can be used as a chemical fingerprint. Over the last 2 decades, element detection by XRF has been enhanced with the use of high-intensity synchrotron sources, making trace concentrations routinely detectable. However, XRF spectral analysis software packages have not kept up. The software is commonly complicated and leaves too much of the detailed handling and combing of spectral data to the human eye. Data analysis is delayed and often not fully interpreted. This also makes it extremely difficult for a non-expert. Since 2017, over 24 students in our research group have analyzed synchrotron micro-XRF data. The students in the top picture were part of a 12-week summer undergraduate research program. They were all able to learn Peakaboo and analyze micro-XRF data from multiple synchrotrons in mineral exploration projects, environmental studies, and archaeometry. Here are 2 examples. The top example is an ancient electrum coin. It is predominantly gold and silver in composition. However, because we collected full spectrum data, we were able to interrogate the data and discovered platinum group element hotspots, which are shown in red. The bottom example is drill core from gold-bearing zones near the historic Con and Giant mines near Yellowknife, showing that gold is associated with the sulfides pyrite and arsenopyrite, quartz carbonate, and sericite chlorite. This work was presented last year. Our graduate students, both MSc and PhD, are now routinely using synchrotron XRF mapping as an early part of their research. They're collecting micro-XRF map data directly on pieces of drill core, as shown in the top photographs. They are analyzing the data to identify key element spatial relationships, as shown below. This is allowing students to then select representative samples for further analysis, including thin section preparation for detailed mineral identification using petrography, EPMA, and other analyses. The proof is in the presentations. Here's a list of presentations coming up during M&M by students who have all incorporated XRF research into their theses. Juliana Casali was awarded an M&M 2020 Student Scholar Award. She will be presenting August 7th in session P10-5. Please check them out. Synchrotron XRF mapping is now a routinely used technique. However, the analysis of full spectrum MCA data remains challenging. Typically, every beamline has its own acquisition software and output file format. Some beamlines want to send users away with finished element maps, but this is done by using regions of interest corresponding to individual peaks. As you can see in the top image, only a limited number of ROIs can be chosen, so this requires detailed knowledge about the sample. And it also means that discoveries like the PG hotspots in our electrum coin may never be made. The software for full spectral analysis that does exist requires expertise, both in software and in XRF. Before Peakaboo, students needed 1 to 2 years just to become familiar with the software. That's 2 years where the data collected is not informing next research steps. And in other software, the fitting of peaks is done by the user, so misassignment occurs regularly. If you can't get your data into the software, you'll never analyze it. Peakaboo is designed to read data in many formats from any XRF system, both synchrotron sources and lab instruments. Plugins are created to open the different file formats. Currently, Peakaboo recognizes datasets consisting of individual single-point scans, text files of rows of numbers where each row represents the spectrum collected at a single spot, and the more complex HDF5 formats, which are becoming increasingly common. New file formats can be added with plugins. Some of the plugins we currently have include multiple beamlines at the APS, at the CLS, and the SIG-Ray AutoMap file format. Every time we use a new synchrotron beamline, we develop a new plugin. The fitting of XRF spectra is a scary prospect. There are so many peaks. Some are for different elements, some are for the same element. How does anyone know? The usual answer, look them up in a table. Well, that's fine when you're an expert. And even then, mistakes are made. Peakaboo has 4 methods: guided fitting, auto-fitting, element lookup, and summation fitting. With the guided fitting, the user clicks on a peak and Peakaboo provides a list of suggestions. Because Peakaboo uses the element's full K, L, and M spectral pattern and does not use a single peak match, the user can see how well the pattern fits. You're not just fitting the single peak. Example 1 shows the fitting of the iron K pattern, including detector escape peaks below the recognizable K alpha, K beta peaks. But if a user doesn't recognize the K alpha beta pattern and clicks on the iron K beta peak to fit, the closest energy is the cobalt K alpha, but clearly the spectral pattern does not match the collected data. The user can try each suggestion until the pattern matches the raw data. In example 2, the user is using the element lookup to add in arsenic. This is very useful if you want to look for trace elements that may be highly localized, like the PGE inclusions in the coin, gold in a drill core sample. Finally, example 3 shows the fitting of the iron plus iron summation. It's important that these processes be recognized and not interpreted as a single element. With the fully analyzed full spectrum XRF data, Peakaboo can rapidly process multi-element 2D maps. It's capable of creating maps containing tens of thousands of pixels over a wide spatial scale, from detailed micron scale maps of single mineral grains to centimeter scale maps of drill core. The results can be displayed as composite maps. The top map is an iron K edge map. They can also be displayed as overlays, like the bottom example, examining the spatial relationship between arsenic and iron. In addition, you can highlight a region on a map for further spectral processing. In the bottom example, I'm highlighting a region. By collecting plot selection, Peakaboo will then take you back to the fitting window to re-examine the XRF spectra. We needed a software package that users could learn quickly, can accept file formats from different synchrotron beamlines and lab-based systems. Peakaboo is freely available, specifically designed to be user-friendly. Since 2017, the modifications have been designed to help new users become rapidly competent in the handling of complex XRF spectra. It offers robust, automated fitting of XRF spectral peaks, increasing the sensitivity to trace elements. Large arrays of spectral data can be processed into maps to define spatial relationships. From the data, users can identify and further interrogate correlations between elements, and most recently, using a multi-element reference material like a NIST standard, quantitative analysis can now be performed. Again, for more on these last two, please check out Stuart McIntyre's presentations. Again, the software is available at www.peakaboo.org. We would like to thank people at the Advanced Photon Source, the Canadian Light Source, and SIG-Ray who supported us during data collection. Stuart McIntyre and Mike Bauer initially developed Peakaboo with funding from Canary. And the software has benefited greatly from testing by more than 24 undergraduate students, partially funded through the Mining Industry Human Resources Council Gearing Up program. Thank you.